The only problem with that is I'd hear myself talking. Okay, chapter 3, instruction level parallelism and exploitation. All right. I took the slides from chapter 3. I cut out all the in-order pipeline, all the out-of-order pipeline stuff because we just talked about all that. We don't need to do it again. I'm just going to go through a couple of extra features that are important for architecture. Basically, what have we done beyond the out-of-order simulator that we just talked about and moving forward. This is important because you will see this for your homework. So pipelining, aka the in-order pipeline, became universal in 85. In order, and then 95 is when out of order really took over. But there's been other enhancements besides the in-order pipeline and out-of-order pipeline in order to exploit parallelism and improve the performance of your programs. There's been basically two main approaches: hardware-based, aka the computer architects are going to solve this problem, and compiler-based, where the compiler is going to try and solve it. Hardware-based ends up usually winning because they can handle a variety of programs effectively. Compiler-based only really happens when you know your program. You basically understand your programs very well. So hardware used in server and desktops, not exclusively P&P processor. Basically, compiler only really works in scientific ones. All right. When exploiting ILP, that's what we've been doing with our in-order pipeline and our out-of-order pipeline. It's the ideal pipeline CLP plus any halls, data hazards, or control stalls. Basically, we want to figure out what your maximum CPI, which is cycles per instructions, which, by the way, can be less than 1. And let's see, parallelism basic block is limited. Typical size of basic block is 3 to 6 instructions. So parallelism for ILP must be optimized across branches, which is also why branch prediction is so important. Excuse me. Basically, we're trying to explain what are the limitations of instruction level parallelism with in order and out of order. It's the fact that your basic block is 3 to 6 instruction, so you have to optimize across branches, which can make things difficult. All right. Other things we've looked at, there's data dependence. Loop level parallelism, we write loops, they execute X number of times. Well, we can unroll these loops statically to get rid of these branches or dynamically. Another thing we can do is something called SIMD, single instruction multiple data. These are called vector processors. Also, this is what your graphics processors do. You have one instruction that can do adds across multiple pieces of data. Very simple example, we have add, which takes 2 registers, adds them to a third. Maybe you have an add that takes 2 sets of 32 registers, does all the add in parallel, and then puts them into another set of 32 registers. So then it's only 1 instruction as opposed to 32 instructions. That's the quick SIMD example. Go a little more into this in a bit. Problem, data dependency, because if you do it in one instruction, you have to make sure all your registers don't depend on one another. And dependent instruction cannot be executed simultaneously, so you can't necessarily do all 32 adds at once. All right, so that's data dependence. What we got? Hardware speculation, execute instructions along predicted execution paths, but commit the results if prediction was correct. Right, so this is what we've been doing with branch prediction. And then you update the register file when no longer speculating. So this slide should not be in here. This is branch prediction. We're going to move on. Multiple issue and static scheduling. So to achieve a cycle per instruction of less than 1, you're going to have to be able to execute more than 1 instruction at the same time.
Oh.
What?
Yeah.
Yep. So statically scheduled superscalar processors be able to statically tell the processor what instructions can be in the execute stage in this functional unit over there, this functional unit over there. That gets very messy very quickly. VLIW, very long instruction word. Basically, you're going to bundle 4 instructions you're going to take 4 instructions and put them together in something called a bundle, and the compiler is going to say that these 4 instructions have no dependencies upon one another. And then that way the hardware can just execute them without having to do any checking. You can also do dynamically scheduled superscalar processors, which is what we're doing with our out of order pipeline. Because we can issue 2 instructions at once. Let me put them together in a nice chart, because I think this will drive it home. Superscalar, just being able to execute or issue multiple instructions. Issue type, dynamic. Definitely you have to do detection via hardware, because that's what's going to do all the forwarding. Scheduling, with the static version, the compiler is telling you what goes into what reservation station when. Dynamic, the hardware is doing it. Distinguishing characteristic, up here it's in order execution, some out of order execution but no speculation, and then the speculated one is all out of order execution. Example of the superscalar static, a lot of MIPS are in old ARMs. Yeah, the dynamic one doesn't really exist, and then the speculative one is basically what we've been talking about with it trying to issue multiple instructions. VLIW, notice the issue is static because you're issuing up to 4 instructions at once in a bundle. Detection is mainly in the compiler, because the compiler is telling you what instructions can be executed. Compiler is doing the scheduling. All hazards determined by the compiler. Most examples are signal processing, like the TI-68, and then Epic, which is basically a version of VLIW. I'm just going to say it's the same thing, is what's done with the Itanium, if any of y'all remember that processor. You remember that? You got one at home? So what's a VLIW? Package multiple operations into one instructions, aka bundle. You might have an integer or a branch, 2 independent floating operations, maybe 2 memory references. What's the problem? Must be enough parallelism in your code to fill out the available slots. If there isn't, what happens?
They're wasting space and
because what gets filled in those slots? Noops. No ops. And then you're basically doing nothing, except increasing your code size. Disadvantage, it turns out to be really hard to statically find the parallelism. Your code size will increase. They found between 30 and 40%. No hazard detection in hardware, so the compiler had to do everything. And then binary code compatibility, because if you want to increase the size of your very long instruction word, you have to recompile all your code. Okay, dynamic scheduling, multi-issue, and speculation. Most modern chips do all 3. 2 approaches. Well, I love how there's 2 and there's 3 dots. That's great. But really, it's 2 of them and then hybrid. First one, which is what we just talked about, assign reservation stations, update pipeline and control, and half clock cycles. Can support 2 instructions per clock. Or you could design a ton of logic and try and get all the dependencies, which turns out to be gross. Issue logic can become the bottleneck because you have to figure out how you can issue as many instructions at once. We don't need this picture because it looks just like the Pentium Pro. Notice you have your floating point adders, multipliers, energy units. Here's your reservation stations. And you have your reorder buffer happens to be up here, as well as your register file. All right. So multi-issue, limit the number of instructions that can be issued in a bundle. 1 floating point, 1 integer, 1 load, 1 store. Examine all the dependencies of a Moong? Wow, that's impressive. The instructions, if dependencies exist, decode them in the stations. Also need to be able to do multiple commit or completion as well. Okay, here we go. Just give me a good example. Good. Load what? Load into register 2. Register from basically the address stored in register 1. Increment register 2. These instructions look funny because they're x86. Store the result. Add 1 to register 2. Store the result in register 1. Then we're going to increment the register 1 pointer, and then we're going to branch if it's not the last element.
This looks like the homework question that I haven't done yet.
Yeah. So if no speculation,
Hey, that's like the dumb graph thing they were doing that didn't make sense with the tomato soup method. Pretty sure that's the exact same stuff.
oh, did I mess up on presenting stuff in the right order?
Maybe.
Okay.
I'm not sure. I'd have to check the question again.
Okay. Yeah.
But that
If I did,
is-
definitely tell me, because then that'll need to be fixed. Okay. Iteration number. This is a loop, so how many times it iterates. Knows that it issues at clock cycle 1 and 1 for these two, 2 and 2, and then 3 for that one. Executes later on memory. And the issue is that the first issue, it needs to wait for the load to complete before it can write it. And we can still add this one, execute directly, and the last store word has to wait for the previous instruction. All right. And this is with speculation. Where am I?
Can you use those instructions with the tomato soup method?
Yeah.
Oh.
See, these are instructions. They work. All right. Notice. Oh, I'm sorry. I'm going back and forth. Notice these slides mess up the columns for you because notice you have write to CDB at clock cycle number, and then when you go over here, it's been shifted over to this column, which is what you want to look at, and commits at clock number. So
What's the CDB?
I don't remember what that one's asking about. But this is the commit, and the file. Well, that's the write to the commit log essentially, and then actually commit it one cycle later. Okay, thanks. But it can wait, it commit in order, no execution delay on this load because it can look ahead after speculating the branch that needs to start the load. Notice back here, it needed to wait for the branch not equals to complete. And what happens as you move on, it's able to speculate and start scheduling instructions earlier. So what is this branch target buffer? Here's another picture in case it was a little harder to understand from my slides. PC of the instruction, that's this index over here, and then the predicted PC on the right. So you're storing the PC of the instruction at register or memory value 100, and then where do you want to jump with the PC? Notice at the end you usually have predicted taken or not taken. Lastly, it's called optimization larger branch target buffer. Add target instruction to buffer to deal with longer decode time. In other words, you have the lookup, you have the predicted PC, you have the branch, and then you have the first instruction that's executed at that location. That way, it can just start executing that instruction right afterwards while it's still trying to load it from memory. So most unconditional branches come from function returns. So just like branch folding, where you store the target, just store the return address there, and you'll be good. Okay, how much speculation should we do? Missed speculation degrades performance and powers relative to no speculation may cause additional misses with your cache and your TLB. Prevent speculative code from causing higher costing misses. You want to make sure speculating with multiple branches, complicated. We did the tournament predictor as well as a hybrid predictor here. All right, nowadays we're getting more and more concerned about energy efficiency because batteries are still pretty much terrible. Unless you like your battery.
Mm-hmm.
You do? How long does it last?
20 years.
On a charge. One charge.
20 years if plugged in.
But if not plugged in?
Like 10 hours if I'm really lucky.
Really? Wow. Speculation is only energy efficient when it significantly improves performance. When it comes to energy, so speculation is good. Value prediction. You can predict what the value is coming from a memory address, but that ends up being hard. No one does it. Because with branch prediction, it's either taken or not. With value, it's some value between 0 and 4 billion. Good luck. Any questions? I was just trying to clean up a couple of things that I might have missed in chapter 3.
So that means the homework's pushed back.
What homework?
The one that's due today.
No, it's not. No other questions? All right. Well, we went ahead and completed that. Bart looks like he's good.